This is 2017 AP Physics2 FRQ. Of course, the question is in electrostatics. The figure above represents four objects with the charges as shown that are held in place at the corners of a square. Point P is at the center of the square, a distance d from each of the objects. Express all algebraic answers to the following in terms of Q, D, and physical constants. On the dot below, draw an arrow that represents the direction of the net electric force exerted on the object with the charge plus Q by the other three objects. Calculate the magnitude of the electric field at P due to all four objects. On the dot below, draw an arrow to indicate the direction of the net field at point P. Calculate electric field. Next bit. Calculate the electric potential at point P due to all four objects. Next bit. In a coherent paragraph length response, briefly describe the meaning of electric potential energy and explain qualitatively how electric potential energy can be related to work. Also explain qualitatively how the electric potential energy of the four object system would change if the plus Q and plus 2Q objects on the right side of the square now switch positions as shown in the figure below. Support your explanation using appropriate physics principles. This is simple. See here, we are supposed to find out the direction of the net force at plus Q. This is the point where we have to find out the net force. So for that, you see, these are the three other forces acting on this force. These two charges are like charges, they repel each other. This pushes this charge that side, this pushes this charge this side. So repulsion. So opposite side, the charges will have to, the charges push the other charges in the opposite direction. This charge pushes this one, this charge pushes this one. Comparatively, this charge is higher, so that resultant between these two pushes will be this side, that I represented like this. Okay, so the resultant of these two forces will be like in this direction. Okay, the force due to plus 2Q on plus Q will be in this direction. Next, force due to plus 2Q on plus Q is from this one, is in this direction. Obviously, no, because this is pushing this one, this is pushing this side. So obviously this side. So these two are the direction of resultant of these two forces. Now we have to find out the resultant of these two. Resultant of these two is this one. This is the resultant of these two. Okay. Now another charge minus 2Q attracts this one. So because attraction means this charge is pulling this side and this charge pulls this charge this side. Obviously, the magnitude is more. This charge gets pulled towards this direction. So this is the direction. Now compare these two. Which one is greater? This is greater now because the resultant of these two forces is this one, and this is the resultant of the attraction. Okay, direction of the resultant force direction, attractive force direction. This is now which one is this is the greater? No, so the finally the direction of the force will be this one. So I represent it like this. Okay. Next, he is asking us to calculate the electric field, net field. So to find out the net field, what we have to do here, uh, the direction of the field is the same as the direction of the force because we know E is equal to F by Q or F is equal to EQ. F is equal to EQ, you know, no. So what is the electric field? Electric field is the force per unit charge. And we know this is infinitesimally small. Its effect on the field is negligible. Its effect will not be felt by the bigger charge. Okay, the electric field is produced by a big charge, and this is a infinitesimally small charge. Actually, Q tends to zero. That means negligible charge. So therefore, the electric field direction is the direction of the force. electric force. Okay, we know F is equal to, we can find out the force magnitude of the force using the Coulomb's law. F is equal to k q by d square. Okay, and then so now we have to find out the electric field, direction of the electric field at P. Am I right? Now, what is the direction? You see, here. This is here. These two, field due to plus 2q and plus 2q. These are exactly opposite, no, in the opposite corners. Okay, so this the direction cancels out, and then this direction, when we consider the direction of these two, because of the electric field due to these two charges only matters. Okay, because these are unequal and then opposite charges. Obviously, this is more. The direction will be in this direction. It is okay. Next, we have to calculate the electric field. So, electric field due to plus Q is equal to, you see here, E is equal to F by Q. Am I right? So, this is the F, and then Q you put here, and then you will get this as the answer due to plus Q. And then field due to minus Q is this one. And then total field. He is asking us to find out the net field. Net field is equal to, add these two, you will get the field. This one. Okay. This is the answer for this one. Next, he is asking us to find out the electric potential due to all the four charges. Here are the four charges, and then we have to find out the electric potential. Okay, so for what is the electric potential? Electric potential is V is equal to ED. Am I right? See here. Um, I will explain this to you. Okay, that is the better one. Electric potential is nothing but work done in bringing the unit positive charge from infinity to the field, or it is electric potential is the work done in moving the unit positive charge from reference point to the required point in the electric field. Okay. So, therefore, P is equal to ED, or V is equal to, instead of E, I will write F by Q. Okay. So, here the notation he given as uppercase Q. That is why I am following uppercase Q only. Okay. So, V is equal to F by Q times D, because work done is equal to force into displacement, or voltage is equal to electric potential, or voltage is equal to ED. Okay, this you know very well. Okay, just now I explained to you also. So, substitute the values here, because F is equal to this one. And then D, and all the values you substitute here. And then what happens here? You are left with V is equal to KQ by D. Okay. Now, for each one, you have to calculate. Suppose if you add all the ones, then what happens? You will get 3KQ by D as the answer. Okay, this is for one charge. So we have the four such charges now. So I have to take the answer like this. Okay, calculate the answer. How to find out the force, and then you substitute here, and then you will get this as the answer. Okay, just a simple, instead of Q, you have to substitute these values. Then you will get the answer. And then next, what he is asking is, he is asking us to find out describe the meaning of the electric potential energy, and asking us to qualitatively relate the electric potential energy to the work. That I will explain to you, and then I gave the answer in writing, and then I will explain to you. Now let us consider there is a uniform electric field between these two plates. One is negatively charged plate, another one is positively charged plate. And then our charge is plus Q, test charge is positively charged. Okay, I'm taking for the sake of convenience. You can take the negative charge also, no worries. Okay, for the sake of convenience, I am taking a unit positive charge here. So because this is a unit positive charge, this is a negative field and this is positive field. This field repels this one and this field attracts this one. So net force is in this direction. Am I right? Now I am trying to move this unit positive charge towards the plate B. This is plate A, this is plate B. That means towards the positively charged plate. For that, what I have to do, I have to apply an external force. Then only I can move the test charge downwards, because towards the positive plate. Okay. Now we know work done is equal to force dot displacement and cos theta. W is equal to FD cos theta. And then F is equal to QE, and then D is D, and then cos theta is 180 degrees because the net force is acting in this direction, and then I am trying to push the positive charge towards the other direction, opposite to the direction of the force. Therefore, theta is equal to 180 degrees, or W is equal to negative QED. And this is nothing but electrostatic potential energy. How it is equal to electrostatic potential energy? Because according to work energy theorem, work done is equal to change in energy. Here it is the electrostatic potential energy. Now the question arises, why not it be kinetic energy? Because the object is moving, it has some kinetic energy also. No, why you are not considering the kinetic energy? I already told you the test charge is in uniform electric field. Uniform electric field means it is not at all accelerating. When the object is not accelerating, the kinetic energy will not change. Okay, the kinetic energy remains same. That is why it will not come into picture. Okay, here only the electrostatic potential energy comes into picture. That is why I am taking this one. Therefore, the energy is equal to, according to work energy theorem, this work done on the positive test charge is equal to change in potential energy, that is less negative because it is moving in the opposite direction. Okay. Suppose if you take the negative charge, okay, negative charge, and it will be pulled downwards, and if you try to push it in the upward direction, you will get the same result. Okay. Just for the sake of convenience, I am taking the positive charge, test charge as the positive. Okay, that's it. Now he is asking us to find out the change when the configuration changes. That means the charges plus q and plus 2q are positions of the plus q and plus 2q positions are exchanged or changed. Then what happens? See here, because of the change in the position of the charges, the net force changes. Am I right? Previously here, the force is plus q and this is plus 2q. So the resultant will be negative, no? Because this is both are same charges, therefore there is a repulsion. Now here also there is a repulsion, but here these two are equal charges. Okay. Therefore, whatever the amount of push it gives to it, it gives the same amount of push to this also. What about this one? It can't give push with the same potential, and then only this direction. You have the downward direction. This gets this it pushes this one, but not get pushed by this one upwards. So downwards this one. And when it comes to this one, again, same way. What happens to this one? This is attracting this one. This is attracting this one. So the same. Okay. So the total force or the net force of the configuration changes. The moment the exchange of charges takes place, the configuration changes, and then the net force of the system changes. When the net force changes, obviously the work done will be different. Am I right? Because work done is equal to F dot D, force dot displacement. Okay, product of the force and displacement. The moment force changes, the work done changes. The work done changes, the electrostatic potential energy changes because work and energy are related. Work done is equal to change in potential energy. When the work done is less, the electrostatic potential energy less, or if work done is more, the electrostatic potential energy is more. Therefore, accordingly, the changes happen. Okay, that is what he is asking. Support your explanation using the appropriate physics principles. Qualitatively, how the electrostatic potential energy of the four object system would change. So this is how it changes. Okay, he is not asking us to give the numbers. Okay, mathematical calculations he is not asking. He is just asking us to give the qualitative explanation. So you write like this: once the force, the charges are exchanged, the total net force of the system configuration changes. Once the net force changes, the work done changes, and then work done is related to the electrostatic potential energy in this way because the based on the work energy theorem, the work done is equal to change in electrostatic potential energy. Therefore, that will also change. That is the answer for this question. Hope this helps. Thank you. Bye bye.